Hi everyone. It's been a while since I last streamed, and part of it has been busyness, and part of it has also been just taking a break from this act of sharing on the internet. But now I feel like it's time to get back into sharing more of my life. And so tonight things will be pretty chill. I will do my homework, which are these problems from Intro to Electrodynamics by Griffiths. Yeah, Griffiths. Yeah, so let's see. These two problems are dealing with Poisson's or Laplace's equations, and the other problems deal with dipoles and linear dielectrics. So, yeah, I think the best way to get into it is to refer to some of the existing materials in the book. And so I just want to solve the problems in sequential order and see where we go from there. And of course, since this homework is intended for work being done over the week, it might not be realistic to solve these in 2 hours, so we'll just try to see how many we can get done tonight. Okay, so now I've located the problem in the textbook. And so it gives me the density of charge for a sphere with radius r. And so one thing we could do is first to integrate this charge to find the total charge of the sphere. But it probably has to do with this unit, which is on multiple expansion. Okay. So this is some result over here. Okay, so it does expansion using Legendre polynomials. Oh yeah, so it gives a generating function form. So it seems like this problem is a direct application of Formula 395. lowest non-zero term, the expansion, approximate potential at large R. And the successive terms tell us how to improve the approximation. So for this problem, we just want to find the first approximation, which should be over here, right? Well, this is just the charge over the distance, right? So maybe we want to include the second term as well. This is the dipole expansion. Okay, yeah, so we're just kind of interested in these two terms. Okay, and here the volume element is r squared sine theta d r d theta d phi. Yeah. Okay. All right. So I guess now we have an idea for this problem, and then we can actually like carry out the calculations a bit later. Okay. Then now we should solve 334. Okay, it says 3-point charges located this figure. So 2 on the y-axis, 1 on the z-axis, and they are all distance a from the origin. The approximate electric field at points far from the origin. Okay, so this should be something similar to, yeah, the multipole expansions. Okay, it has a dipole moment. And this is just a displacement vector. The monopole potential is not quite correct for this configuration. The exact potential is just charge over distance, but here it's this distance r instead of the normal r. Well, of course, since we just have like 3-point charges here, we can like bash the actual answer, right? But we kind of want to do it in this fashion. And then we can also just do like a superposition of these 3 charges. And we also want to find the E field. Okay, it seems like this formula is quite effective here. So 30103 is perhaps the formula we want, but the initial setup here is a bit noteworthy. Okay, so Wait, the electric field? Yeah, I mean, this is just like the result of taking the potential. Okay, so this is set up so that P is at the origin and points in the z direction. This is given by figure 336. Okay. So I guess the question is, how do I apply it in this scenario when I actually have 3 charges instead of 1? Okay, so the dipole moment is kind of um, like your weighted average type thing, except it's working with displacement. So kind of like mass multiplied by distance. So I want to find the actual dipole moment of the system. And to do this, I just take the sum, right? Yeah, just take the sum of R and then charge. Yeah, and 3/100, right? So that would be the dipole moment. Which in fact, since like the two charges on the y-axis sum to 0, I'm actually only left with the moment pointing in the positive z direction. Yeah. Okay. And so then I can actually just like straight up use this formula that is 3/103. Yeah. Okay. So I guess that provides the idea for 334. Problem 334. Okay, so now we can move on to problem 4.6. And now I'm interested in finding the torque on this dipole P. And there's a grounded conducting plate. So I think you could exploit using like method of images. Okay. Okay, so it talks about dielectrics, induced dipoles, then what? Like alignment of polar molecules. So kind of like polarizability. Okay. If the dipole is free to rotate, which orientation will it come to rest? Well, let's try to solve this. Okay. so the dipole experiences a torque. It is given by P cross E. Okay, so I kind of also need to figure out the electric field due to this grounded conducting plane. So do I need to solve Poisson's equation? Perhaps. So the torque wants to make sure the angle between P and E is small, right? So it'll rotate it to that like angle. The field is non-uniform. There'll be a net force on the dipole. Delta E. Delta E is equal to the divergence force is also given by the divergence, where this is kind of like written as an operator. That makes sense. Okay, so to solve 4.6, the big idea is to find the electric field. And then you can just apply the formula for the torque, which is 4.4. So the question is, how do we actually find this field? Right, and so this may be tempting to use like Poisson's equation with the boundary condition. And the boundary condition here is that the potential at x is 0 and y is 0. Oh, okay, the potential at z is 0. Or if we like consider z like independent of the picture, then we just know that the potential that's constrained when x and y can move freely is 0. So if we set z is equal to 0, yes, so we could do this, I guess, with separation of variables. I wonder if there's like some existent result I can just look up. Okay, and then 4.7 wants us to calculate the energy. Show that it's the dot product between the dipole and the electric field with a minus sign. So it'll probably be like a similar mechanism as the calculation process for the force and for the torque. What's an an ideal dipole is just like, yes, so we can always use like the classic setup that's in figure 4.5. But then how would we find the actual energy here? Right? Is this due to like the electric potential energy? Well, in this case, like the constraint on the system is that the two charges are separated exactly by the distance d. So normally, like you would take right for like 2-point charges, this would be kq squared over distance. And so q, oh yeah, and then you just rewrite it. So then the field is kq over distance squared, and then p is q times distance. So that kind of deals with the problem intuitively. Now we want to see how the calculation actually rolls out. Okay, so that's kind of like the sketch for 4.7. We can first move on to like read 4.10 and 4.11 to get a better idea. Okay, so a sphere of radius r, it's a polarization. Okay. So we want to find densities, charge densities, and electric fields. So then we can also give this section a read. Okay, so on polarization. So the polarization is defined as the dipole moment per unit volume. so we can take an infinitesimal piece and then integrate it to find the potential. This is in 4.9. Okay, and then there's actually some fancy stuff going on here. Yeah, you take the gradient of the displacement vector of 1 over that to get r hat over r squared. Then you write this in terms of integration by parts. Okay, then you use the divergence theorem. Okay, and since P is independent of R, okay. So now we define the surface charge here and the volume charge there, which is just P dot n hat and the negative gradient, the negative divergence of P. Okay. And this is due to the formulation in 410. What this means is that the potential polarized object is the same that produced by volume of charge density plus surface charge density. Okay, so then kind of like the idea is we find sigma b and rho b, and then we just use Gauss's law. Yeah. And then since we're dealing with a sphere, it's actually highly symmetric, so it wouldn't be that hard as well. Some uniformly polarized sphere. Okay, so we also kind of understand the mechanics for 410 now. Let's read on 411. Carries a frozen in uniform polarization parallel to its axis. So this would be convenient to use cylindrical coordinates. Find the bound charge and sketch the electric field given different parameters. Okay, so this is kind of just like a calculation problem similar to the one above. And so I guess overall, I would say most of the problems in this homework are applying formulas from what we already have. Okay, so then I guess we can type up the homeworks. So let's try to do just that. Okay. Okay. Let's do this. First, let's let Gemini type up the problems. Yeah, man, I haven't talked to a microphone for so long. This is greatly impacting my ability to speak in front of the screen and really my confidence in talking to a computer. But I'm going to restart the podcast soon and going to be interviewing guests again. And so I feel like this is a necessary practice. Like, talking to a computer screen is quite different than talking to real life people because really you just sit in front of a screen and there's not that intrinsic connection or motivation to talk. And many times, like, people just don't talk. Okay, let's accept this. Yeah, I mean, Gemini tends to deliver quite well. Let's also open up the solution PDF. Okay, yeah, this is nice. All right, and then I will move this over for reference. And we can start typing. Okay. Okay, the question is, do we use 398 and 399, or do we use 395? I think we want to use 395. Okay, let's find the charge first. And so we just take the density given by this, and then we rotate that. So Q is equal to int V of, let's just keep it like that, and then dV, where dV is the volume. Okay, so let's first rewrite this in an align environment. And add this alignment so that we can now type. We can just copy this for now. So we can absorb the sine theta terms into a sine square theta, and then we can take away the r squared terms in the denominator. Now let's try again. Okay, and then we can also eliminate the d phi terms, right? Since phi is kind of independent from everything else. And so this also just simplifies into 2 pi. What about the rest though? Kr squared are both constants. And then we also have an independent integral, so we can just split up the sine squared term to over here, d theta terms as well. And then now we just need to evaluate. So sine squared we simplify into 1 minus cosine 2 theta divided by 2. And this just becomes theta minus sine 2 theta over 2. Whoops. take away this 2 over here. And we add the evaluation bound 0 pi. And for over here as well, this is just a polynomial though. So we have big R, little r, minus r squared. And so for this term over here, we get pi minus 2 pi over 2. So sine 2 pi is just 0, and then sine of 0 is also 0. So then we just get pi, right? Yeah. So we get pi from this term. And then from that term we actually get 0. Wait, okay. That's understandable, yeah. So then we do end up getting 0 for the charge, since this term over here evaluates to 0. And so now actually calculating the dipole moment becomes important. So now we want to use the formula in 396. So the total charge is indeed 0, and we want to find dV can do like an approximate. Okay, the question is, what is this alpha doing here? Like, how's alpha defined? Right, is alpha just like some random angle? It's the angle of separation. So if we look at this diagram, okay, so if r is like really far away, right, then how do we consider this angle? Well, then it would be approximately 90 degrees, right? Since then the displacement r is almost as large as the actual r. So then in this case it would be equal to cosine alpha would be approximately r prime over r, right? Yeah, okay. So we can visualize that as r prime squared over r, and then we just take the 1 over r term outside the integral. And then we plug in what do we plug in? Oh yeah, so here r prime is actually the formula. Yeah, since we're dealing with rho r prime. So this will actually all work out nicely because now we have terms that cancel. Yeah, okay. Where's my window? Okay, here's my window. Where's my cursor? Okay, my cursor's back. Since r is much greater than our point of interest is situated Okay, we're going to further simplify this. So now we want to basically argue that this is almost the exact same thing as what we have seen above, except not quite. And so just going to get rid of this approx sign. And also these square brackets. Actually, I didn't need to do that. And then, so this is just for integrating. We had previously, this is just integrating rho, which is going to be almost identical to this part, except you have a quadratic term already for your distance. So I'm going to expand that, get rid of v here, and then I'm going to replace this part with that. And then I'm going to add, change all the small r's to r primes. Prime actually to the fourth, then dr prime. Okay, and then this will simplify immensely. First we get rid of this denominator term, and then in fact we actually just get rid of kr squared altogether. We throw that over here. Nope. Okay, let's just compile real quick. Oh, what happened? Yeah, the align environment always works in a funny fashion. So now we get rid of this fourth power, change to a square power, and then we also change this into sine squared theta. Yeah. Okay, and then we can also absorb this into prime squared prime to the cubed power. Okay, and then we separate the integrals. So 2 pi d phi 2 pi sine squared theta d theta. And then now we copy the results. So actually we can just simplify here. So this d phi term just turns into 2 pi. This pi term, right, this takes away the 2 pi and instead gives you another pi. Right? Yeah, right. And then this becomes r prime cubed over 3 minus r primed to the 4th over 4. Frac and I don't think this is going to be 0 this time, but I could be wrong. Okay, and then we finish this evaluation. First of all, we just turn this into pi squared. Okay, so this just becomes r to the 4th minus r to the 4th. So we get r to the 4th over 6. And then we simplify. So the pi term cancels out, and then we get a r to the 6th term. Actually 24, right? And then we get r to the 6th pi. Yeah. Okay, as a sanity check, do we have the correct units? Well, this thing has units of r to the 4th. That is of r to the cubed in its denominator, or no, in its numerator. The question is this normal? Not quite sure what to expect. Yeah, I mean, I'd say, like, this is good for now. Let's move on to the next problem, shall we? Okay, so for 334, you want to first cite that the dipole here is actually okay. Include the two lowest orders in the multipole expansion. Okay, how do I expand beyond this? Oh, okay, so this was the dipole field. And so we also want to consider the monopole field. Right, but the monopole field is, yeah, the monopole field is just negative q. Yeah. maybe we can do something similar here. And this is just in the R direction. Yeah. And we can also simplify this. So that P is now given by YA. And then the resulting. Then we just observe. Okay, first off, I should rearrange. Like this, and then just absorb everything. So that would mean, what would that mean? So we first take out the 4 pi epsilon naught, and then we just include everything, brackets. So then it should be YA over R cubed. Okay, this is the R hat term. Let's move it before the hat term. Okay. Yep, this is it. Let's solve 4.6 and 4.7 a bit later, and jump straight to 4.10 and 4.11. Okay. Did I define this? Oh, okay. Defined as the negative gradient okay. So the question is, where is the unit vector pointing on a spherical surface? Right, the unit like outwards vector. And well, this is completely in the r hat direction, right? Yeah, this is in the r hat direction. Let's study how they did it with 4.2. Okay, so polarization in this problem is uniform. It's actually a big difference with our problem because the polarization is not uniform. But why theta? Okay. So, oh yeah, because uniform just equal to P and pointing in the z direction, right? But in our case, it's just pointing radially outward. So it should be the same thing. Yeah, I'd say so. With our case. And then we can also look up the divergence in spherical coordinates. Okay. Okay, and so the actual value is just equal to kr. Yeah. Um, and then okay, whoops, where did that go? Okay, let's go here. Okay, kr r hat. So AR is just KR, right? And then this is just 3 kr squared, which is equal to -3. Okay, quite expecting that. Then we I was actually not expecting this to be just a constant. Well, I mean, it kind of is what it is, right? Negative 3k, and then frac 4/3 pi r cubed is equal to, oh yeah, let's change this into an equation. So negative 4k pi r cubed. Right. The surface area. Okay, why did I delete that? Is 4 pi r squared. So the total electric field is what is this equal to? It's kr cubed. 2 pi. 2k pi r cubed. Negative cosine. So cosine 0, 1 minus cosine pi 2. Right? Let's try again. Cosine pi is negative 1 minus cosine 0, so negative 2, negative positive. So Bound charge. The bound charge on the surface should be 0, except for like the top and bottom surfaces. And then the bound charge inside, right? We can assume the cylinder arranged symmetrically. Its axis on the z-axis and can model it. Okay. And then we just this part does not need to change. This part does need to change. Our polarization is given uniform z-axis. So equal to P at Z. Radial surface of the sphere. The direction of the surface. So the surface on the B top, B But wait, like, how do you deal with this? then isn't the volume part just equal to 0? Since z is not explicitly dependent. I don't know, this is rather confusing. L much greater than A, L much smaller than A. Okay, I think I'll need to debug this. But at the same time, yeah. Okay, so I can leave it as is for now, and then I'll probably come back to work more on this tomorrow. But yeah, okay, this is the first stream of many. I will probably be trying to I'll probably try to stream as much as I can, and also get back into video production, and also into podcasting. Well, I hope you guys have a great night, and see you all.